Hi folks, this is question 2 from the more optimization problems sheet. And it's a pretty typical question relating to economics where we increase the price of an item and it'll decrease the number sold, and we try to find that perfect balance that'll maximize revenue or profit. So if we take a look at A, they're actually asking us to maximize the revenue. So let's take a look at what's going on. Currently, they're selling 1,000 televisions at $450 each, and the research shows that if you decrease the price by $10, they'll sell 100 more units every week. Okay, and we want to use this information to maximize the revenue. Okay, so first of all, let's start with defining revenue. So the revenue is the number of units, okay, multiplied by the price per unit. Okay, so since we're going to be changing the price, the number of units that'll be sold will also change. So here we have two variables, and as usual, we want to try to write this so that we have revenue written in terms of only one variable. And one of the ways in which to set up this problem is to choose your variable that you're going to use is actually neither one of these. Okay, you choose a third variable, and you're going to use that third variable to describe each of these two values. So what we're going to do is we're going to let x be the number of, in this case here, since it's price drops, we'll call this the number of price drops. Be the number of price drops. Okay. Could also be price increases. So here it seems as though this changes in a linear fashion. So every time I go up by $10, go down by $10, the number of TVs goes up by 100. Okay, so keep in mind X is the number of times we drop the price, okay, not the actual amount we're dropping the price by. So let's see if we can use this variable to describe both of these values. Okay, so if you think about the number of units, well, you're starting with 1,000 televisions, okay, and we know that as you drop the price, the number of televisions is going to increase. So we're adding to the number of televisions sold. And every time I drop the price, the number of televisions go up by 100. So if I drop the price once, it goes up by 100. If I drop the price twice, it'll go up by 200. Three times, go up by 300. So we see here that we've got a linear relation that describes the number of units. It's 1,000 plus 100x, 100 times the number of price drops. Now we can do something similar for the price per unit. Okay, right now they're being sold for $450. Okay, and every time we have a price drop, well, the price goes down by $10. So I drop the price once, we go to 440. If I drop the price twice, we go to 430. It goes down by 10 every time. So we can write this as 450 minus 10x. Okay, now what we've managed to do is come up with an equation for revenue which uses only one variable. Okay, the other thing I notice is that if I were to multiply this out, I get a quadratic function. Okay, not just a quadratic function, but if I look at the leading term, that is the one that's going to give me the x squared, I see that this multiplication will have a negative a value. So it makes sense to be talking about maximum revenue as opposed to minimum revenue. Okay, so now our goal here is to take this function and to determine, in this case here, the number of televisions they would expect to sell at that price and the price they have to charge to maximize the revenue. Okay, so notice how we already have this in, well, almost factored form. The revenue is factored. Okay, it's not in official factored form. So one thing we could do is FOIL this out, put it in standard form, and then complete the square to determine the maximum values. But of course, we know we can also do this by finding the zeros, the x-intercepts of this function, and then averaging them out to get that x value. Okay, I think that in the end, that's the quicker way. There's a lot less algebra to do. So let's do that here. So we have to solve the revenue being 0. We want the x-intercepts of these here. So that means either the first expression has to be 0 or the second expression has to be 0. So we've got 1,000 plus 100x equals 0, or 450 minus 10x equals 0. So here, if we solve for this, 1,000 goes to the other side, becomes negative 1,000. Negative 1,000 divided by 100 is negative 10. Here, we'll bring the 10x to the other side. Okay, so we've got 10x equals 450, and 450 divided by 10 is 45. Okay, so these are the x-intercepts of this function. Okay, and if we want to find where the maximum occurs, we know that the x value of the vertex is given by the average of the x-intercepts. Okay, so to find the x value of the vertex, we'll average these out. So negative 10 plus 45 divided by 2. Okay, so that gives us 35 divided by 2. So we've got 17.5. Okay, so what does this mean? This means that in order to maximize revenue, okay, I have to have 17.5 price drops. Okay, so that means, well, let's figure out what that means. Now, let's go back to the question and see what they're actually asking us for. So based on this research, determine the price the sales manager suggests they charge and how many televisions they have to sell. Okay, so notice here that we are not looking for the actual maximum revenue. If I was looking for the maximum revenue, well, I'd take this x value and put it back into my equation to give me my maximum revenue. But that's not actually what I'm looking for. What I'm looking for is the price that we should charge. And remember that we wrote an expression for the price based on x. That's our 450 minus 10x. So our price is given by 450 minus 10 times 17.5. And I'm sure we can do that in our heads, but let's just check that out with our calculator here. So we've got 450 minus 10 times 17.5. And so that gives us $275. Okay, and the other thing we have to determine is the number of units we're going to sell. But again, remember that the number of units, we already have an expression based on x that gives us the number of units. So here, number of units for maximum revenue is going to be 1,000 plus 100 times x, which is 17.5. And so here we have 1,000 plus 100 times 17.5 equals, and they're 2750. Okay, so what we have here is the price and the number of units that need to be sold in order to give us maximum revenue. So let's just do a recap of what we did. First of all, defining revenue as number of units times the price for each unit, product of those. Okay, we let x be our number of price changes, the number of times in which I change the price, and with that variable, I was able to write both the number of units and the price per unit as a function of that one variable. Okay, it turned out to be quadratic, that opened downwards. Okay, and since it was already factored, it made sense to find the x-intercepts, okay, average them out to get the x value of the vertex, and that was in fact enough to determine what I needed to determine. Had I wanted the actual maximum revenue, I would have taken that 17.5 and substituted back into the equation. Okay, so I'm just going to pen out because the next step is to look at part B. Okay, and